Greetings everyone. Today we're going to explore graphing exponential growth and decay. And this is in our enriched Algebra 2 class. It would also work for Algebra 2. If you're looking for an Algebra 1 video, you'll want to see my other playlist. So let's talk about exponential growth and decay from an Algebra 1 perspective though. And so growth and decay is something that's continuously increasing, continuously decreasing, and very real world applicable, even as basic as bank interest. Bank interest can be considered growth. We're gaining money. Population could be growth or decay, right? We saw a boom in North Dakota many years ago, but it can also decline or decay. Uranium is decay. Depreciation of your car, oh my gosh, talk about, you can't get any more real world than that, right? You lose money the moment you drive it off the lot. And then carbon dating. Carbon dating might be something that you can connect with from your other classes as well. Visually, what's really nice about growth and decay is the visual graphs that we're going to explore have a very specific shape. And I always like to say it's almost like the curve of your hand. If you hold your hand with your thumb straight out, your right hand will show you a growth curve. And if you hold up your left hand, it will show you a decay curve. And we're going to stick to these curves. Now, can they be wider or skinnier and shift? Yes, that's what we're going to explore in this unit. So let's talk about the function. Now, we've been working on so many functions in our Algebra 2 class that this is just right along the same lines. First of all, wherever your x is, you have a horizontal shift, right? So we also have to remember that it's the opposite of what we have. So if it says x minus 2, it's plus 2. You still have your vertical shift being added or subtracted on the outside. And then what's going to change? Oh, you still have your a value. A value is your vertical stretch or compression. That's still used in the same way. But what's new is the parent. The parent is going to be this base. Now that base can change. The base of an exponential function can be an integer or a fraction, or we're even going to explore some letters. And so the base is the parent function. And how do you know? You know if it's growth or decay from the moment you see it. If the b value is greater than 1, even 1.0001, it is a growth function. If your b value is between 0 and 1, then it's decay. Any type of fraction decimal value. Now, we're not going to deal with negatives as in relation to saying it's growth or decay. And also it can't be exactly 1 or exactly 0. Now, let's talk about parent table. So far this year, our parent tables, we could just memorize them. One parent table, memorize it, done. That's not the case. So we need to make this little note somewhere. You have to create your parent table each time using whatever the parent function is. You have to create a parent table each time. Why do I say that? Because I might give you 2 to the x. That's different than if I say 3 to the x. That's different if I say 1/2 to the x. Those are all parent functions, right? There's no transformations happening there. But how this 2 creates a table, how this 3 creates a table, and how this 1/2 creates a table, they're different every time. And so there's no, could you memorize a lot of the basics? Probably, but I would stick to just planning on creating a parent table each time. So let's see what we mean here. First of all, some details in our notes. My parent function is the base to the power of x, I should say. Type, because the base is 2, 2 is greater than 1, so it's growth. Okay, we're going to answer the rest of those questions later after we get a visual aid. Let's create our parent table. Now, for our parent table, we are going to stick to the same 5 easy x values, meaning the smallest integers possible. And here's what we have to create. I'm going to take this 2. Okay, let's do the easy numbers first. If I take a base of 2 and I say 2 to the second, I get a 4, right? And I'm actually going to do some color coordinating here. 4. 4 is my parent table. Okay, let's take 1. 2 to the 1. That's 2. That's my parent table. Okay, let's take 2 to the 0. Wait, what's anything to the 0 power? 1. So every parent table will have 0 to the first. You can rely on that because that is a true property. Oops, I forgot a negative there. What's 2 to the negative 1? Let's talk about that. We're dealing with a negative exponent, which moves the base to the other side of the fraction bar. Okay, well, what if I have 2 to the negative 2? Now, what's in green, I don't need to see that, right? You can calculate that mental math. I'm just showing you where I'm getting it from. 2 to the negative 2, well, that would kick it to the denominator. And then when it moves to the denominator, 2 squared is 4. What is written in black is our parent table. Parent table is in black. Okay? Now I'm going to color coordinate. We're going to approach our transformations the same as we always have. We read left to right. The first thing I see is 3 times my parent table. We multiply the y values by my a value. Nothing new there. And that's the only transformation I have. We're starting off a little more simple. Okay, so let's do some calculations. We get to keep our x values. And I'm going to work backwards. 12, 6, 3, 3 over 2. Easy fraction work. 3 over 4. Let's plot. Let's see what happens. Negative 2, 0.75, right? Negative 1, 3 over 2 is 1.5. 0, 3, 1, 6, and 2, 12 would be up here, right? A lot of times you're going to have a value that goes off. That's fine. Now, first of all, acknowledge the shape. It does look like the curve of my hand. Second of all, notice my 3 is where I cross the y-axis. My 3 was also my a value. That will also always happen. So your a value determines your y-intercept. Unless we shift. So let's mess with that next, but let's connect our dots. We have a true growth function. Asymptote. Asymptote is determined by a horizontal line that you will never cross, and that is always determined by your vertical shift, which I don't have one, right? So if I don't have one, the x-axis, or the value of 0, my asymptote is a horizontal line, y equals 0. Domain. Domain is forever left, forever right. My range, I have an asymptote, right? It's 0, then comma infinity. We approach 0, it's an asymptote, we never cross it, so it will always be a parentheses. All right, let's take a look at this next one here. First, I want to acknowledge my parent function is the base to the power of x. My type, it is decay because 1/5 is between 0 and 1. Let's create our parent table. We're going to start with the same 5 x values. What's anything, any base to the 0 power? 1. Start with the easiest, right? That's guaranteed. What's anything to the first power? Itself. What's anything to the second power? You might have to think about this one. Let me draw a little sketch. 1/5 to the second, that's saying 1 squared over 5 squared, right? So we would get 1/25. Now, I showed a little work. You don't have to if you know that or if you're using a calculator by chance. How about to the negative first? Let me think about that. 1/5 to the negative. That'd be 1 to the negative 1 and 5 to the negative 1, which would just flip both of them. 5. It's 5. All it did was flip. And so a fraction to the negative 1 will always be the flip. How about negative 2? Isn't it the same as 2 but flipped? So sometimes the patterns are nice and easy to work with. All right, let's apply our transformations. I do not have an a value that I need to deal with. All I have is this +1 that is a vertical shift. So that's a +1 to my y values. Let's calculate our final table. 26, 6, 2, 1 1/5. I would say stick to a mixed fraction on these ones. That's easy. And 1 1/25. Okay, make those calculations as easy as possible. So -2, I'm way up high, can't even draw it. -1, I'm at 6. That makes more sense. 0, 2. 1 1/5. At 2, I'm at 1 and 1, tiny number, right? And so now, if I use the shape of my hand, I have the perfect decay function. But notice what I'm approaching. Very specific. We have a vertical shift of +1. Because it's +1, my asymptote will be at y equals 1. Your vertical shift will always be your asymptote. Okay, you can rely on that. So that's something you could memorize. So notice how our starting point, our y-intercept, is at 2. And that doesn't really match what we see, right? Why? Because we shifted. Because of that shift, okay? Domain, guess what? Domain's always forever. I know it doesn't seem like much. It looks like we're going up, but we are slowly going left every time. My range, we approach 1 and go to forever. Look at how that vertical shift affects so many parts of our graph. Okay, those were to start us off, Algebra 1 level growth and decay. Now let's jump to Algebra 2. Let's apply every possible transformation we can. Oh my goodness. So give yourself some space for your table here, okay? First of all, parent function is the base to the power of x. My type, it is growth. So I already have a picture in my brain of what this might look like, okay? Asymptote, I'm going to fill that in right away. It's always going to be y equals your vertical shift. Yep. Guess what? Your domain, it's always forever. Now let's see what we can do here. Oh my goodness. Okay, I gotta make my table a little bit bigger. I need some workspace. So -2, -1 still start off that way. What's anything to the 0 power? 1. What's 2 to the first? 2. What's 2 squared? 4. What's 2 to the -1? 1/2. Some of you will start to memorize these quicker. What's 2 to the -2? Square it and flip it. So 1/4. Okay. Those you have to make or create or think about each time. But is there a pattern that you can start to memorize? For sure. All right, I'm going to try to color code. So first thing I see is a -1/4 out front. That's your flip, your vertical change, and so we multiply just like we always have. This process is not new. If it is, because you're not from my class, then you'll want to seek out my other videos. We're going to multiply the y values by -1/4. Next, I see a +1 with the x, so that means we subtract 1 from the x. Yep, it's still opposite. Now, I always said what's in parentheses. Technically, those are contained in the exponent, okay? And my last piece is a +3, so we're going to add 3 for my vertical shift. Now, from there, I want to see that transformation table work. From there, if you straight use a calculator and your fraction key, that's fine, but you do have to be able to do the mental math too. And so we've got -3, -2, -1, 0, 1, easy. Ooh, I'm gonna start at the bottom. It looks easier. 4 times -4th. That's -1. -1 plus 2? Excuse me, -1 plus 3, 2. I was thinking ahead. 2 times -4th. Double the 4th, which would be a half, and throw a negative on it, -1/2. -1/2 plus 3 is like 3 minus a half, so 2.5. Times 1 is itself, so negative fourth plus 3. So if I take 3 and I subtract a fourth, I've got 2 and 3/4. Let's see. Half of a negative fourth is a negative eighth. A negative eighth. That would be, 2 and 7/8. And it's meeting my pattern, right? I'm also using my pattern to help me here. A fourth times a fourth is a 16th, a negative 16th. So 3 subtract a 16th would be 2 and 15/16. Oh my goodness. All right, let's see what that looks like. Negative 3, 2 and the tiniest bit ever. Or 2 almost to 3. Sorry, I said that wrong. 15/16 is almost 3. Oh, well, let me erase that. Okay. So I'm right here. Negative 2, I'm at 2 and 7/8. It's actually a little less. Negative 1, I'm at 2 and 3/4. That's 0.75. Negative, or excuse me, 0, I'm at 2.5. 1, I'm at 2. You guys, I'm not comfortable, like, I don't see that drastic jump or drop. And so I'm going to just take a moment. I'm just going to try this 3 out quick. If I was to plug in 3, 2 to the third, sounds kind of crazy, right? That'd be 8. And I'm just going to apply this because I want more information. If I don't have a calculator and I'm not sure, let's try that out. Negative, or a fourth times 8 would be 2, and then negative 2. Negative 2 plus 3 would be 1. So, oh, and 3 minus 1 would be 2. At 2, I'm at 1. Okay, I'm starting to see that curve. You could, I'm just throwing it out there. You don't have to draw this, but you could go one more. 2 to the fourth would be 16, right? Maybe this gives you more understanding of the graph if you just go a couple more out. So that would be at 3. That makes sense. 16 divided by 4 is 4. Throw a negative. Negative 4 plus 3 is negative 1. 3, negative 1. There. Now I'm seeing that curve, right? So if you don't see what you want to see, okay, add some more values. Or. We already knew it was going to be shifted left 1, didn't we? And so maybe you don't have to use negative 2 through 2. Maybe you already know how you should shift that. All right, so let me go draw what we got. And then, poof. Now you might be really confused, but Mortvet, we said this was growth. We are growing from left to right. We are growing in the negative direction. The negative direction. What things grow in the negative direction? The national debt is growing in the negative direction, like it can happen, okay? And so my domain is still true. My range is based on that asymptote. Did we meet the requirements of that? Yep, that makes sense. But now my range, I start at negative infinity, least to greatest, and I go up to 3, approaching 3. So it makes sense, right? So if you don't have enough information, create more information. Alrighty, so how are we making this even more Algebra 2 level? We are going to introduce you to a whole new number that maybe you've learned about in maybe like a science class, but it's been a while. So let's talk about Euler's number. Euler's number, first of all, I want you to pause and grab your calculator and go find the E button, E. Now, if you are using a scientific key or calculator, you're going to find it over here by this LN key. You have to press second and get to it. If you're on your graphing calculator, the TI-84s and such, it's sort of down here in the bottom left. Okay, I should have put an image there, sorry. And what we want to do is we want to see what E is. What is it approximately, I should say. So press second and then get that E pulled up. It's going to ask you for an exponent, and so we want the parent number. Anything to the first power is itself. So you're going to want to type in a 1. And then also, I put an equal sign here. It should be approximate because this number goes on forever. So it's approximately, I'm going to write down what all my calculator says. You might be thinking, well, there's a pattern there. Kind of. It's not exact though, right? And so it's pronounced Euler. It's after Leonhard Euler. I probably said that wrong. My apologies. It's an irrational number. Okay, so think of it like pi, right? Pi is a number that has a formula to get to it. Pi is a crazy number that goes on forever, and it's irrational because there's no pattern, and it can't be written as an exact fraction. Now, just like we have a formula to get us close to pi, we have a formula to get us close to Euler's number. And this would be the formula. And so as you use a larger n value, you get closer to the value of Euler's number. And so just that last part there, just try plugging that into your calculator. Just mess for a minute. You can even pause if you need to. But I just decided to try 100,000 and see what it could get me to. Be careful if you do use your calculator. Your parentheses are going to matter. Okay? And so I'm actually typing this in as I speak because I want to triple check. And on my graphing calculator, I can see when I type in 100,000, it gets me to 4 correct decimal places. So it's getting me closer. The larger the number, the closer you get. And so Mortvet, why do we need to know a new number? Because Euler's number is a base. It's a base. It's an exponential. And so let's take the exact same approach, except we're going to make this way easier. Okay? First of all, parent function. My base to the x power. That's my base. Okay? Type. Well, we just said that Euler's number was 2.718281828. 2 is greater than 1. So guess what? Euler's number is always growth because it's always 2 point something. All right? Let's create a parent table, and we're going to use the exact same values. Now, here's how we're going to make it easier. I don't want you writing down a million decimal places, people. So, anything to the 0 power, even Euler's number is still 1. That's locked in. Okay? E to the first is e to the first. E to the second is e to the second. I want you on your parent table, because you're going to have to use a calculator to write it like that. Okay? That's what I want to see for parent table work. I don't want the crazy decimal because then you're using a rounded value. Let's apply our transformations the same way we always would. This says subtract 3. So from my x's, I'm going to plus 3. And I have a vertical shift of plus 2. So let's do plus 2. And let's create our final table. So we've got 1, 2, 3, 4, 5. Super easy. Let's do the easy one first. 3, 3, 3, 3, 3. Okay. Now as for this, okay, I want you to type it in using the E calculator. So if I go E to the first, get out of the exponent key in case you're using a graphing calculator, and then add 2. Now if you start to memorize that decimal, awesome. I'm going to say, I don't know, 2, 3 decimal places is probably good. Graphing wise, you're only going to use 1. So let's actually just do 1. How about that? What I like to do if you're using a graphing or scientific calculator is I like to go back up to the original and then just change that exponent of 1 to a 2. Save yourself some typing. 9.4, I'm going to round. Okay. Again, go back up. You might have to start over since it's a negative, whatever's easiest, right? But practice using your calculator. Make sure you know how to type it in and get the same values. Oops, I'm going to round this and say 4. And E, I'm typing this in with you, so make sure you're getting what I'm getting. 2.1. All right, let's graph that out and see what we have. 1, I'm at 2.1. 2, I'm at 2.4. 3, I'm at 3. Oops. 4, I'm at 4.7. 5, I'm at 9. Oh my gosh, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice I gave you kind of specific size graphs for a reason. And you know what? We could still answer our asymptote question and draw our asymptote, it is still based on your vertical shift. This still makes sense of approaching and never crossing the 2. Make sure you cruise along the asymptote, and then exponential growth. Make sure you never cross the asymptote. Make sure you go always out to the left or to the right. Okay, don't curve back up. That would be incorrect. So like some students, let me show you in red here. Some students get sloppy and they go, woo, don't do that. That's not growth, okay? Make sure it looks accurate. All right, negative infinity to infinity, as always. And now my range, we are approaching to and increasing forever. Let's try one more. We got to practice this E. This is a new number and a different style of parent table, really. My parent is still e to the x. It's still growth. I'm going to take care of that asymptote right away. It's still negative 2. Y equals negative 2. My domain is still forever. I can still rely on all these things. I'm still going to start off with the same. Oops, what am I doing? Negative 2. Totally wrote backwards there. Negative 2, negative 1, 0, 1, 2. E to the, I don't want the decimal value. I don't want you to actually calculate the starting. Okay, let's just acknowledge that it'll be a calculator problem there. And now let's type in. All right, negative x, negative 1 times x. What? This is new. We have never in a parent table had a factor of x. We are multiplying the x by something. We are multiplying the x by something. What? This is different. Okay, let's see what happens. Minus 2. Is my assumed information still correctly assumed? I don't know. Let's see what we get. Positive 2, positive. Uh-oh. This is changing things, you guys. So let's see. Let's use our calculator again, or if you look at previous problems, maybe you already have all these values, but we got negative 1 locked in, right? 1 and then minus 2. Make sure you get out of the exponents. So I'm getting 0.7. I'm just going to do 1 decimal place. To the 2, and then a subtract 2. 5 point, I'm going to round 4. Let's go e to the negative 1 and then minus 2, negative 1.6. And let's repeat that process and let's do negative 2, negative 1.8 or 9, right? I'm open to that decimal. Interesting. Okay, so at 2, I'm at negative 1.8. At 1, I'm at negative 1.6. At 0, I'm at negative 1. At negative 1, I'm at 7. 2, 4, 6, 7. Oh, 0.7. Mortvet, I can read. Sorry. 0.7. And at negative 2, I'm at 5.4. That's how I knew I was wrong, because I'm like 5.4. That doesn't make sense. 2, 4, 5.4. Okay. So it still has that sort of shape of my hand, right? Oops, that's a bad curve. Try that again. I still see that I'm decreasing. Interesting. Okay. Is my asymptote still correct? Yes. That looks like I'm just going to keep approaching 2, negative 2. So I was correct there. My domain, still good to go, right? We are still going forever left and forever right. There's no restrictions on what our x value can be. My range still plays out the same way. So we're approaching negative 2 and we're going to forever. But now, let's reevaluate something. Is this still growth? It is. It is still growth. We're growing in a negative x direction. We're growing to the left. We're growing to the negative domain. Okay? The base is the base no matter what. The negative changed the look of our graph, but it's still growth. right? That's a little bit trippy to think about. We are growing, so put your finger on the far right of the graph and trace to the left. Trace negatively, and we are growing. All right, so welcome to exponential functions. I need to see parent table work. As always, nothing's new. I need to see that on any practice we do and assessments. Become more familiar with E using your calculator. Okay, be comfortable with that. Let me know if you have any questions. Check out Google Classroom to see what our tasks are. And until next time, have a good one.